All right, so we're going to look at a couple different varieties of blower controls that we experienced in the lab this past week. The first one is going to be on the 2015 CRZ. And you can see that at the top right-hand side of this diagram, we've got two pins called out between the inlet and outlet of the blower motor. Pin 2 is a white wire that acts essentially as the power supply through the blower motor relay, protected by a 30 amp fuse number B57, and then ultimately protected by the main 100 amp battery terminal fuse on this vehicle. This has a permanent ground for the coil. The ignition switch supplies fused power for the coil of the relay. For the high amperage side, again, this white wire feeds to the blower motor. So essentially what that means is that anytime the key is activated through the ignition 2, energy is supplied to pin 3 of the blower relay, which in the MICU provides a pass-through point for ground on the coil of the relay. Now when I activate the blower motor, I'm going to go through the blower control or the HVAC controller on the dash. They're calling it the climate control unit. What this does as an input is supplies a variable path to ground at pin 1 through what they're calling the power transistor. A power transistor is an electronically activated switch, so it is not a mechanical switch. It is taking a process input, converting that request to a indication of how much on time we want of the blower motor, and this assembly provides a diversionary path to ground, as you can see is located on G502. So when you all performed the test on the blower motor for the Honda CRZ, you were monitoring two things. One was the energy being consumed essentially by the blower motor. The second thing was the amount of current flowing through this path. So if we look at this from a waveform perspective, channel A is energy concentrated on the blower motor. Channel B is what? That is current flowing through the blower motor. So at a low speed, actually we'll go from an off speed of around 0 volts being consumed by the blower motor. You can also see that we have essentially no current flow at this point. The circuit is open, no energy is being supplied to the resistor, being the blower motor itself. This is demonstrating the amount of energy concentrated just on the blower motor and not on the ground side through the power transistor. No amperage, no voltage being consumed. We go to speed 1, we're diverting around 3.8 volts to the blower motor, which means that the ground side of the blower motor circuit is labeled right here between pin 1 out on the blue feed through the power transistor assembly and ultimately back to ground. The amount of energy remaining on that ground side is around 8 to 9 volts. The initial on also forces that brush DC motor to momentarily stall. You can see the inrush current on channel B, which is amperage, hits 9.7 amps because the motor is physically stalled, and then the motor starts to spin. We've seen similar behavior take place on a brush DC motor in a starting circuit. The maintained current flow for this particular circuit at low speed is around 2.4 amps. So again, this is off, off, low speed, low speed. You notice that every time we make a request to increase the speed of the motor, we get a spike in amperage, spike in amperage, spike in amperage over and over and over again. So effectively we have off, then we have 1, 2, 3, 4, 5, 6, 7 speeds that the blower motor operates at in this vehicle. You can also see that when we go to the second speed, amperage goes up, the amount of energy concentrated on the engineered load, being the blower motor, also goes up. So now we're at about 5 volts dropped on the motor. Our current flow levels out at around 3.5 amps. We go to our next speed. You can see that we're flowing about 5 amps. We're also dropping around 6.5 volts on the motor. Next speed, we get a rise in amperage again because we're adjusting the resistance effectively in the circuit through the power transistor, 8.1 volts, and we're flowing around 7 amps. Next speed, we're hitting almost 10 volts of energy consumed. And from there, we're seeing about 10.6 amps of current flow. And this progressively goes on the rise. So effectively, we get to the point where we get to the 7th full speed. We're pulling a pretty serious amount of amperage, almost 15 amps continuously, at a voltage of around 13.63 volts. All of this happens, again, by the controller dictating from the input side on what they're calling the climate control unit, the amount of energy concentrated on the blower motor itself. So this power transistor is acting effectively as a resistive path to ground continuously while this motor operates to adjust perceived speed. In the case of the 2008 Highlander Hybrid, the blower controls are a little different than what we noticed on the 2015 Honda CR-Z. I want to pull up the factory diagram. When the group got down to the blower motor assembly, the front blower motor assembly on this vehicle, they noticed pretty quickly that there were 3 wires going to the blower motor, 3 terminals and a 3-pin connector attached to the blower motor. The white wire feeding in was a direct connection to a 50 amp fused circuit from the battery box. That is called B+, that's battery positive voltage. The white with black wire at terminal 1 coming out of the blower was a direct path to ground. And then terminal number 2 was a red wire which connects the front blower assembly to the AC amplifier assembly. This assembly right here is essentially your input as an operator of the HVAC system. Essentially what occurs, you select the blower speed request by pushing a momentary contact switch on the dash for fan speed up or fan speed down. That signal is then diverted through terminal 23 of the AC amplifier assembly through the red wire to terminal number 2, or the signal or input to the front blower motor assembly. Now this signal, when recorded, is a little unique. This capture shows us channel A here is our signal input, and channel B is actually the current flowing through the blower based on selective speeds. So you can see if the signal is resting high, meaning I don't want blower to operate, that signal input is seeing about 5 volts. And that's pretty common for a lower power circuit as an input, a 0 to 5 volt reference. On the same waveform, we look at the opposing channel, channel B, and we've got around 0 amps. I'm going to go ahead and mark that at 0. So we have 0 amps flowing through the motor. Now from this point, selectively, as we increase the request for fan speed, we're going to take a look at this signal in a moment, we also get an increase in current flow. So we've got 1, 2, 3, 4, 5, 6, 7 tiers of fan speed available in the 2008 Toyota Highlander Hybrid. Now, I want to zoom in for a moment to this portion of the capture to see physically what's taking place. If I zoom into this 0 to 5 volt range here on channel A, we're going to go a little closer to this signal. And what we can see in this signal, if we actually go and measure one cycle event, I'm going to go here, the beginning of one waveform, and I'm going to go to the same falling edge on the next waveform. You can see that's about a 500 hertz signal. So this says 496 hertz. Hertz is an indication of the amount of times the signal generates from high to low or low to high per second. Across the board, if I get rid of this zoom, you're going to see thematically, that says it's about 2 milliseconds. Thematically, if I go to another area at a high speed, we're going to zoom in. We're going to zoom way into this capture. You can also see here on this capture start point roughly to the beginning of another cycle roughly. If I open this ruler, you can also see that we're around 2 milliseconds and the frequency is the same. So what is changing? Well, specifically what is changing is the amount of time the pulse width is modulating. So each one of these elevations vertically across the screen, up and down, up and down. While they operate at about a 500 hertz frequency, the amount of time the signals being pulled low, pulled to ground, is increasing as I request a higher fan speed. So again, the frequency, the cycles per second remains the same, but the amount of time that that signal is present to ground actually varies, or the signal that's high varies. So if we want to validate that, I'm going to get out of the zoom screen here. We're going to go use a math channel function. So I want to look at what's happening with channel A, because again, I can see that as I go through and I increase the speed request over time, the amount of time the component is being pulled low goes up pretty significantly. So zoom way out here, and I'm going to go to math channel, and what I want to find is the ability to activate a negative duty cycle for channel A. Again, this is being pulled to ground. That 5-volt signal is being pulled to ground. The more it is being pulled to ground, the higher the fan speed. So I'm going to hit negative duty for A. I'm going to drag this math channel feature in. Eventually it will buffer. We may have to make another capture here. I'll show you the ability to do that. I'm going to turn this off. I'm going to go to add, and I want to go to scientific functions. I want to go negative duty, signal A, hit next, and we'll set the color as a contrasting color again. I'm going to hit finish. What this should do is generate a pattern indicating how frequently the component in that signal from channel A is being pulled to ground. So in this perspective, a negative duty cycle, you can actually see the more time the component, the signal, is being pulled low correlates to the amount of current flow in the circuit. It also correlates to specifically the amount of time within that 500-ish hertz frequency. Sorry, we're using a lot of data here on the computer to do a zoom function. Give it a zoom. Maybe. My computer does not like the processing power necessary for this. We'll keep zooming, keep zooming. Okay, so this is what I want to look at. How long at a high speed are we being pulled to ground on the SI circuit? So here we're being pulled to ground across this time frame. The difference between point A and point B is around 1.5 milliseconds. So 1.5 thousandths of a second roughly. Now to validate the argument made earlier, I'm going to drag this monitoring area from the higher fan speed request to the lower fan speed request. I'll drag my cursors over here, and you can see the amount of time we're being pulled to ground here. Earlier we were at 1.5 milliseconds roughly. Now we are at 671 microseconds. So what that indicates to us is that there is a correlation between the time the SI is being pulled to ground and the response from the blower motor to increase or decrease speed. And this has to go back out to a broader zoom So essentially, with the negative pulse width modulation calculated, we can see the lower amount of time we have grounded, the lower the fan speed. Increase the request, slightly higher amount of time, higher current flow, indicating higher perceivable fan speed. Progressively, this happens through the SI circuit.